we're looking at this story of quantum trajectories in a somewhat more richer circumstance than we looked before. We're looking at atoms now that have are real atoms, atoms that generally have some degeneracy, a multi-level structure. And so in particular, we're just looking now at the situation where our atom has some total angular momentum quantum number, which we're generically calling J. Okay? Could involve electron spin, electron orbital, could involve nuclear spin, whatever it is, all. Sometimes you call it F if it's everything, but generically call it J. And there's physics underneath there, and we know that if you have such a situation, if this is a electric dipole allowed transition, then there are dipole selection rules, and these atoms can have transitions between these different sublevels based on those selection rules. So the dipole selection rules tell us that the total angular momentum quantum number here can be the same or changed by 1, and the projection of the angular momentum along any axis can stay the same or change by 1. Okay? Of course, there's an underlying other parity rule that is part of the dipole selection rule. The orbital angular momentum has to change by 1 if it's a dipole transition. So you go from S state to a P state, or P state to a D state, all of that stuff. All right. So these levels are the eigenstates, typically with respect to some axis that we call the z-axis. Okay, and that's chosen by us, however we choose to do it. And these transitions, these particular transitions, are driven by a dipole which is oscillating in one of 3 ways. Either it's oscillating linearly along the quantization axis, in which case we call that a pi transition. That's when the n quantum number doesn't change. Or the dipole is rotating either clockwise or counterclockwise, right-handed or left-handed with respect to the z-axis, in which case we drive transitions, if it's right-handed, that go from here to here, increasing n by 1, those are sigma plus, or the other way are sigma minus. All right? So with that, we just kind of wrote down without derivation the master equation. And the master equation is in the Lindblad form, where now the jump operators, we have more than one jump operator corresponding to spontaneous emission of a photon, which corresponds to these 3 possible radiations that could happen if the dipole is oscillating linearly or in those 2 orthogonal ways. And so these jump operators here, scaled relative to the total spontaneous emission rate, gamma, take me from the excited state to a ground state, weighted by the Clebsch-Gordan coefficient that describes the conservation of angular momentum going from that level to that level, okay, or vice versa. And so those are the jump operators, and then this is the master equation in the Lindblad form with the effective Hamiltonian as in the standard way. And when you sum over all these dipole operators, they're like the sigma plus and the sigma minus, now with multi-levels, you get the total projection onto the excited state, okay? And so we could do, for example, a Monte Carlo simulation of the kind that we've discussed to get a quantum trajectory, where you would say, if the atom is there a jump? Meaning, is there a spontaneous decay of the atom from the excited manifold to the ground manifold? And that probability, that probability for that jump to happen in a small time interval, delta t, depends on the probability to be, the total probability to be in the excited manifold. And then which particular jump happens is given by the standard formula. These are my jump operators, and that depends on the Clebsch-Gordan coefficients for a particular transition. Okay? So with this structure, we're looking at an interesting problem, the problem of coherent population tracking. So that problem is the one we studied last semester, in which we're looking at a situation where we're driving this multi-level atom with some coherent polarized laser field, polarized in some way. And what we found last semester is that when the level structure is of a particular kind, that the system will ultimately, in steady state, land in a dark state. The dark states are the states that do not absorb. They do not couple to the laser field, okay? And so in particular, we're looking at this kind of level structure where both the excited manifold and ground manifold both have total A momentum 1. And these are the Clebsch-Gordan coefficients, okay? So in particular, we're looking at an example, though this example we'll see in a moment how this generalizes, where my laser field is polarized along an axis that we're calling Y. We can call it whatever we want. I can call it Z, I can call it X, I can call it X plus Y over square root of 2. It's linear. I'll just call it the Y-axis for now. Okay, that's just a label. And that that vector is a linear combination of these two circular with respect to the Z-axis, okay, with this particular superposition given here. This minus and plus is important in the whole deal. Okay, so in the rotating wave approximation, we're on resonance. This is my Hamiltonian, okay, involving in this case, because this is polarized perpendicular to the quantization axis, we only have sigma transitions. We have no pi transitions. So we drive absorption in superposition of sigma plus and sigma minus, okay, with the same sign. Okay. And so in this case, I'm very calm today, and this chalk is stronger than last. In this case, we only have sigma transitions, so we can drive a sigma plus or a sigma minus from that, and we can drive a sigma minus and a sigma plus from this transition. Okay, so these are, I'm going to denote these levels by, just to emphasize the fact that we're representing the atomic angular momentum as being eigenstates of projection along the z-axis. So let me just call this n sub z. So it's a -1, a 0, and a +1. And these are the transitions that are driven by the laser field. Okay? Now, we can have spontaneous emission, and that spontaneous emission can take me like that, or it can take me like that, or it can take me like that, or like that, or like that, or like that. But it can't take me like that because the Clebsch-Gordan coefficient vanishes. Okay? So that is just not an allowed transition. So what that means is that if the atom starts in either this state or this state, it always comes back to plus or minus 1. It can't get to 0. Okay? Because the laser field can never get it there. There's no pi light. This is not allowed transition. So if we start in the subspace spanned by these two states, then we always stay in that subspace due to both the coherent field as well as the spontaneous field, right? Now, in this particular case, there is, so if we look at that, then we can decompose the system instead of these three levels into a slightly different basis. And what we see, if I just look at, okay, just look at these, the transitions where I'm staying in this, I start in this subspace. This Clebsch-Gordon coefficient is -1/√2, and this Clebsch coefficient is +1/√2, which means that there is a state which is the dark state. The dark state, D, is the, in this case, the symmetric superposition of mz equals +1 and mz equals -1. That state is such that it's not coupled by the field, right? Because these two paths, if you like, destructively interfere. There is an orthogonal state, which we call the bright state, which is the antisymmetric combination of these. And that state is coupled, okay? So if you're in the antisymmetric superposition, then these constructively, because of that sign, interfere, and then we'll end up here, and then you'll spontaneously decay, either this way or that way. And then there's a state C, which is the mz equals 0. But then, if I start in this, the bright, dark subspace, I stay in the bright, dark subspace. All right? So, what we're looking at, what we know is that if we start the system anywhere, it will ultimately, in steady state, get to the dark state. And we want to understand, we want to analyze that and think about that a little bit in the context of the a particular unraveling of the master equation in quantum trajectories. Okay.
And it's dark state is defined for the ground state, right?
Well, if it's in the excited state, it's not going to be dark. It's going to spontaneously emit. It's a state that, if it's there, will not emit any light. But you can, I mean, and that's always going to be one of the ground states. Yeah.
So when it's spontaneously decaying,
Yep.
then we have equal probabilities to go to either dark state or bright state.
Correct. So I'm going to review that right now. Talk about that a little bit more in detail.
Dark state will not absorb, but while decaying, it can come through.
Well, let's go. Let me talk about it in a little more detail, and you can ask your question a little bit more. Yeah.
So the Clebsch-Gordon coefficient corresponding to the central, the 0 to 0 transition 0.
Yep.
But why, is there like an easy way of seeing why that is?
There should be, I just
Okay.
don't have it.
Okay.
It's easy for somebody who's thought about it, and I did at one point, but no, I don't know the answer to that.
Okay. Because again, what's the physical situation with, we're going from a j equals 1 to a j equals 1, but is what's changing between the two different manifolds there? I think you talked about this last time, but.
Well, I mean, what it is the addition of angular momentum. Remember what this Clebsch-Gordon coefficient is. So that particular case is the Clebsch-Gordon coefficient. Okay, so I'm adding, remember, you can add angular momentum with total angular momentum 1 with total angular momentum 1 and get to angular momentum 1.
Okay.
The case where there's 0, it turns out, and I know this is true, for reasons that probably have, and absolutely must have, I think, a reasonable physical interpretation. When you go from a J, If you go from a J to a J,
Mhm.
but you try to add 1 unit, then the projection's 0, that addition, there is no amplitude for that. So it's going from the uncoupled representation of angular momentum to the coupled representation of angular momentum. And this particular addition coefficient vanishes. Why?
Okay, yeah.
Okay,
And
sorry.
and this has to come with, you know, this situation where you have additional 2 or 3 or maybe even number of Jordan coefficients that that cancel each other, that have, you know, opposite signs and magnitude. If you have the situation where one of the transition is
It
comes
vanishes?
with, yeah, comes with 0 probably.
I don't, there's no, I mean, you're saying, is there always a dark state corresponding? Yes. Okay, so we're gonna, that'll become clearer in a moment. Okay, so the fact that, yeah, let me come back to that. There is a connection. The fact that this vanishes is connected with the fact that there is this dark state.
Equals to,
That these
equal
cancel
amplitude, yeah.
is related to this.
Okay.
Okay, that is one and the same thing in a way that you'll see momentarily. Okay, so let us consider the following. Suppose at t equals 0, we prepare the state in, for example, the mz equals +1 state. Okay? That state is an equal superposition of the dark state and the bright state with a 50-50 probability and that particular amplitude. Okay? So now we start the system there and we drive it. Okay? Well, what's going to happen? What does our quantum trajectory formalism tell us? Well, in a given time interval, delta t, we can ask, are you going to jump or are you not going to jump? So we're going to drive, this is like the damped Rabi oscillation problem that we studied before, but now it's not just that it can come back to the same level, it's going to start driving into the excited state, and depending on the probability to be in the excited state, it's going to have some probability to spontaneously emit. And we can ask, in that interval, delta t, jump, no jump, jump, no jump. And if in a given time interval we don't see a jump, then we update according to the according to the non-Hermitian evolution, right? So if we see no jump, well then the state gets updated a little bit in the non-Hermitian evolution. And what's going to happen is we're going to, with some, I'll say it goes to, we'll start adding a little bit more to the dark state and taking a little way away from the bright state, normalize. Whatever it is, something like that. Okay, so if I don't see a jump, the non-Hermitian evolution will be such that it's going to take away a little probability amplitude from the bright state and put it in the dark state. Because if I'm not seeing a jump, it's more likely to be dark. Now, that's just saying it, but that's what the math will do. If you take either the -I h effective t and put it, all that stuff with the laser field in there, I mean, you have to do, both, you have both the damping part and the Rabi part. It's like the damped Rabi problem. Okay, so I mean, of course, it gets someone's excited. So I'm saying this is what, if I just look at the probability just to be in the dark state. If I jump, though, well, there's two kinds of jumps. I could have either a sigma plus jump or a sigma minus jump. And Gopi, this is what you were I think, asking, but I'm just kind of guessing, so I'll get through this. If I'm up here and I spontaneously emit a sigma plus, well, then I end up in this state. And if I spontaneously emit a sigma minus, I get in that state. So if I jump with sigma plus, then psi goes, let's say if I jump with sigma minus, then my jump goes back to where I started. Okay? Which is again,
Plus one.
The superposition of bright and dark. Okay? If I spontaneously emit a sigma plus photon, then my state, this one's plus one. Yeah, that's, yeah, sorry. Then I go to the minus one. And then I'm in the other superposition. But in either case, I'm 50-50 bright and dark. And then I'll go to the next case and say jump, no jump, jump, no jump. Okay. So, how do I get to the dark state? It's through the not observing a photon. It's that measurement, the not seeing a photon result. The null result is the only thing that could get me to the dark state. So if I were to simulate this, and you will if you do your homework for extra credit, you will find that if you look at this problem and you look at, say, the overlap of your system with the dark state as a function of time in a particular realization, well, it starts 50-50. 50% is a probability to be in the dark state. And then, you know, there's some period where you don't see emission, and then all of a sudden it jumps, but then you're halfway there again. And then maybe, you know, you get to there, and then it jumps, and then, you know, maybe this trajectory gets you all the way there to the point where you never jump again.
Why can't you continue like that forever?
What do you mean? Continue like what?
Jumping back to one.
You could,
Okay.
but the probability gets smaller and smaller and smaller. I mean, it can happen. I mean, the time to take to get to the dark state is infinity. It can. So, but those are extremely rare trajectories. But it's not forbidden that happens. It's just that it becomes less and less probable when the probability amplitude in the dark state is 0.9999999, and this guy is, you know, 0.1. So it just becomes less and less probable. So you average over many trajectories, and you'll see the solution to the master equation that we saw before. Yeah, Bob.
Would it be possible to, I guess, use a different unraveling of the master equation so that we actually do get to the dark state via jumps?
Yes, that is the next, that's where
okay.
we're headed. That's kind of the whole story here. So I'll get to that in just a moment. Yeah, Jonathan.
Have we averaged over the gravity oscillations that we're doing? Is that what that is a product?
You mean why is this going back and forth? Those.
No, I mean, and why isn't, like, we're not staying in the, we go up to that other state, right?
Right.
Sometimes.
Up to the zero state.
Yeah.
Yeah. Yeah, what I'm plotting is just the I think the particular case I'm looking at is where the saturation, where gamma is just huge. The saturation probability is tiny, so that the probability to ever get to the excited state is small. Remember, I'm just looking at a case where gamma is big compared to omega. But otherwise, because otherwise, this is like an overdamped Rabi oscillation. Otherwise, you're right. I will see many, many, many oscillations. Because, you know, if you remember, I mean, if we look at the two-level situation, you know, what we have is down for all the oscillations. But if your Rabi frequency is tiny, then it looks more like this. You don't actually ever oscillate.
Yeah, but a trajectory still oscillates.
No, you would never see it. We get there.
And so, I mean, in this situation, it's also a little bit more complicated than standard Rabi oscillations, right? Because we've got kind of three relevant states that are.
Yeah, I mean, but it is true, Jonathan is correct, that if your Rabi frequency was very, very big compared to your spontaneous emission rate, you would see you go into here well before there's some high probability, so it would oscillate back and forth before it would spontaneously emit. But I'm looking at the particular case here where gamma is bigger. I mean, gamma is bigger.
Okay.
Right. Okay, so now, with foreshadowing in hand, we want to consider a different unraveling of the master equation. What does that mean, a different unraveling? Well, a different unraveling can be thought about as having done a different measurement on the environment. Formally, it means a unitary remixing of the Krauss operators that got us the Lindblad map. But that is equivalent to thinking about a different measurement that was being done. So what was the measurement that was implicitly done here? The measurement that was implicitly done, so the particular choice of Lindblad operators corresponded to a measurement of the photon in the spherical basis E0 E plus and minus is Ex plus or minus I y equal root 2. Okay, and Jacob, as you brought up, what this really means, and let's think about this just a little bit, what does it mean to measure a photon in this basis? What it's, recall that, you know, what we're doing here is thinking about the photon that is emitted when the dipole oscillates in one of these three ways. Okay, so if the dipole oscillates along the z-axis, then the photon is coherently emitted into a dipole radiation pattern. It's not emitted into a plane wave. It's emitted into a superposition of plane waves that has this pattern of radiation that you all know and maybe love. On the other hand, if the dipole is rotating relative to the z-axis in the xy plane, what does the pattern look like? You guys know? Well, that's if it were just oscillating like this, but it's in a circle. Some of you took 511 with me, and remember the peanut shape dipole pattern, radiation pattern. It's kind of the superposition of those. Remember that? y-axis. It's kind of rotated around. Okay? So, and, along this axis, it's either pure circular this way or circular that way. Along these axes, it's pure linear. Along any other axis, it's elliptical. These things have names. They're called vector spherical harmonics. They're in chapter 16 of Jackson, at least the second edition in CGS units. This is an x1, 0, and these are x1 plus or minus 1. They are the vector spherical harmonics. They're functions of theta and phi. They're the kind of, and they're vectors. So I don't know how you do this measurement, but these are orthogonal functions over the sphere. That is to say, if you integrate these over the sphere, you get delta. So this is the kind of orthogonal measurement that one is imagining. One can't measure a plane wave, one has to measure the whole wave function. I don't know how you do that measurement, but it is an orthogonal measurement that in principle could be done by someone who understands optics better than I, and there are many. All right, fine, little diversion into E&M. But now, what's really the point I want to make? Let's imagine that instead of measuring the photon in this basis, I'm going to measure the photon in a basis that's rotated by 90 degrees. So I'm going to, instead of looking at the photons relative to the spherical basis here, I'm going to analyze the photon relative to this spherical basis. I'm going to call the E0 axis EY, and then E plus or minus equal to minus plus that's a perfectly good way to analyze the problem.
Should one of those be an EZ?
One of those should be an EZ. Which one should be EZ? EX goes to EZ, EY goes to EX. EZ goes to EY. Thank you. Okay, then it's EZ. So that's fine. We could do that. It just means that, we just rotated all these things to the y-axis. Okay, well, relative to that, what it's saying is I can look at the process, then I'm going to look at the y quantization axis. Since I've chosen E0 to be EY, and look at the atom with respect to, I'm just going to look at those processes that are most easily described by, instead of looking at the atom's quantum numbers relative to eigenstates of Jz, I'll look at them as eigenstates of Jy. I can always do that. So the atom has the same structure. And it's still true, all of those same Pledge-Gordon coefficients are the same. However, in this case, the laser field is along the y-axis. Nothing's changing about the physics. The laser is still pointing along y. I'm just analyzing the problem differently. Okay? So given that the laser is polarized along the y-axis, what transitions are driven in this problem?
The zero.
The pi transitions. So I can go from here to here, the laser, and of course it can't do anything there because there is no transition, okay? And if I decay, I can decay like that, I can decay like that, I can decay like that, or I can decay like that, okay? Fine. Now, the master equation that describes this is the same master equation, but with a different set of jump operators. Okay? So if we could find new jump operators. I'll call them d tilde, which is a unitary rotation of the old ones. That takes me from the z-axis to the y-axis. Really, I should call this is really the Wigner D. There's just too many D's around because it's the representation of the rotation group in the spherical basics, which is usually called D. But I'll just call it U. Okay? And of course, if you plug this, or vice versa, the dagger, you'll get the same master equation. So the master equation is the same. It's just with respect to a different set of jump operators. This is what's called a different unraveling, or a different. So these set of, plugging this, I claim that if I do this, that this master equation, it's easy to prove because these are unitary. It's the same master equation. It's just now written with respect to a different set of jump operators. That this equals that. Okay? So, but now our jump processes look different than before. Okay? So, what's going to happen in this problem? Well, firstly, what is the dark state in this problem? Just looking at it. Zero. So the dark state is my equals 0. But of course, the dark state is the dark state. It's not, is it the same state? Well, in order to know that, we need to know how are the eigenstates of Jz related to the eigenstates of Jy. We have to apply the rotation operator to get them. If you do that, you get the following. So let me write a little. The state with j equals 1, my equals 1 is equal to 1 over root 2, j equals 1, and z equals, forgive me if I allow myself, all of these are for j equals 1, so I don't want to have to write down j equals 1. I promise that. So my equals plus 1 is equal to a half mz equals 1 plus I root 2 mz equals 0 minus mz equals minus 1. My equals 0 equals 1 over root 2 mz equals 1 plus mz equals minus 1. My equals minus 1 is 1 over 2 mz equals 1 minus I root 2 mz equals 0 minus mz equals minus 1. Okay, so that's just a change of basis. Now notice, as it must be, this state is the dark state. So that's what I was alluding to, Amir, which is that the fact that there is this state means that in some other basis there's gotta be the case that there's this interference effect. That's saying this state, which is the state that can't go, is the state that has the destructive interference in the other basis. They are indicators. The bright state in this case is the superposition my is also my equals plus 1 plus my equals minus 1. That's equivalent to the state mz equals plus 1 minus mz equals minus 1. Okay? And then the state, which is the antisymmetric state, is the state which is not coupled once I start in the basis of bright and dark. This is the state mz 0. Right? Maybe there's a 9 there, but it doesn't matter, it's an overall phase. Okay, so now this comes to Bob's point. What happens in this unraveling of the system? Again, we have a basis, but the physics is the same at some level. We start in in this case, as before, we start psi equals 0 in the state which is a superposition of bright and dark. Okay. So this is equal to, relative to the y basis, is this. It's the superposition of this state and this state. The bright state is plus my minus 1 over 2. Right? So relative to this basis, what we have is we start with half the population here, and then the superposition of these two guys in the my basis. Okay? Now what's going to happen? Well, I start driving the system, right? And again, if I don't see a photon, then the same kind of quantum trajectory occurs to start. So again, if I look at the amplitude or the probability to be in the dark state as a function of time, I start with half the probability to be here. And I start, for some time I might not see a photon. And I start rotating out of the bright state and into the dark state. But then what happens? Well, I can suppose that I spontaneously emit a pi photon. Well, if I spontaneously emit a pi photon, then what happens is I start here. I had equal superposition of this and this. Where is it? Here it is. Right? And then I end up with the same amplitude up here, and then I can't tell from the pi photon whether it started from here to here, so I transfer the coherence back to here. However, if I see this photon, I know it wasn't in that, because that state sure couldn't have emitted, because there is no electrochromic coefficient here. So I've projected the system totally onto the bright state. There is no dark state component. The dark state doesn't do anything here. And I don't, unlike in the case of the sigma, where I ended up in equal superposition of plus and minus, here, I'm totally bright. So if that happens, I'm here. Okay, so now it can absorb and emit for a while. Perhaps for a while it's going through that. There's no probability amplitude to be in the dark state. But then eventually, it might be the case that it emits a sigma photon. Say it emits a sigma minus. What happens then?
Jumps to 1.
It's totally in 1. And stays there forever. So it's a totally different quantum trajectory. But again, if you average over many, many, many of them, you have to get the same thing, because it's the same master equation. It's just that the unraveling is quite different.
Actually, this picture is a bit more intuitive than the other one.
Maybe, you know. I think, well, so I think this is interesting on many layers, you know. What really happened? Well, in some sense, it doesn't make sense in quantum mechanics. What is true is that these photons are entangled with the states of the atom. And we can look at that entanglement in different ways. And depending upon how we end up measuring those photons, then gives us an instantiation of this. But it's not right to say that either this jump process happened or that jump process happened. Yeah?
Is there being different unravelings dependent on any property of the system? If there's only one jump operator, is there only one unraveling?
That's a good question. And the answer is no, and we're about to do that. Right. So what, um, before I get to that, let me just make one other small point. It's just kind of interesting, vaguely interesting, something that came up years ago when this was first looked at and realized this was an example out of Balibar, Moore, Castan stream of research on this, which is that from the numerical point of view, although this is less relevant because we rarely use quantum trajectories in this sense as a numerical tool for solving the master equation, although these two unravelings are in principle equivalent in the limit of an infinite number of trajectories, some are more useful than others when you have a finite, when you're doing a simulation and you only have a finite. And you can kind of see that they're going to have huge fluctuations in this guy relative to the case that it slowly, coherently rotated into it. So from a numerical perspective, they're different in the finite sampling sense. That's kind of something you'll see in your homework. All right. Very good. So, what I want to turn to for our very last topic here is to the problem of quantum state diffusion. Okay? And what I mean by that, what we're going to study in the next few lectures, is the unravelings that we've looked at so far. The quantum trajectory had two kinds of pieces to it as we've seen them so far. We have weak measurement corresponding to the null result. So if we got no photons in these cases, then the measurement didn't do much. It did something, but it was weak. And then we have these jumps, which gave us a lot of information and changed the state fairly drastically. Okay? So the way our imagined measurement record was, so this gave us a strong measurement. What we want to look at is unravelings that for all times is weak, even when we are getting some, say, spontaneous emission, for example. We want to think about a different kind of way of examining, measuring the system, such that at all times we do only small changes to the state. Okay? So to do that, we're going to develop a little bit of formalism, and we'll just begin that formalism, I guess, today, and continue it next week. And then we have our bonus lectures, of course, starting this week. Right. All right, so let me begin. So what we're going to do is develop a formalism to do this, which is going to involve what's called the stochastic Schrodinger equation. All right, so how are we going to get at this? Let's go back and think about the general formalism, how we derive the quantum trajectories from thinking about CP maps, differential CP maps. Okay? So we have our Lindblad map, which tells me that can map that in this way with what we call Krauss operators M0. And MU. Right? That's our Krauss map where MU we wrote as L mu square root of ET, and M0 is 1 minus I over H bar, whatever the Hamiltonian is, ET minus 1/2 sum over mu of mu dagger of mu dt. Okay. So that's what we had, and then we have a way of generating this map by throwing dice or throwing darts, and then having them have the statistics such that many ensembles gives us this convex combination. Okay, so we have with probability dp mu given by this, we make the state jump. Okay? Or we could say in unnormalized form, psi just goes to this. Otherwise, psi goes to 1 minus I over H bar, H effective dt, psi, unnormalized. So we can write this as a sort of formal differential equation. Okay, so let's call d psi tilde at t plus dt minus, right, so this is, I'm calling this psi tilde now, the unnormalized guy. The tilde I'm using unnormalized. Okay? So what I see here as I write this as follows. This is minus I H bar, H effective dt, I tilde, plus sum over mu, dn mu as a function of t, L mu minus 1. Okay. Where I've introduced something new. These dn mu's are what we call stochastic intervals. So this is not a deterministic differential. It's a random differential. And this differential, dn, takes on the following, has the following properties as written so far. dn mu of t is equal to 1 with probability psi of t rather mu psi mu dt and 1 otherwise. Okay.
And it's differential because the probability is
Differential because of dt. Yeah. And this clearly satisfies, we want these to be independent. So for different ones, this is 0. They're uncorrelated. And when they're the same, well, dn squared is, if it's 1 or 0, it's the same thing. So this is equal to dn. When you square it, you get the same thing. You get, because it's 0 or 1. Okay? And clearly, this also, if I average this over realizations, well, I get the probability dp mu because of these probabilities. Now, this differential equation is not linear. It looks linear, but it ain't. Because dn depends on psi. So this is a nonlinear equation. Okay. All right. So I can write that also, if I like, and I do like, in normalized form. We're going to kind of go back and forth between the unnormalized and the normalized form, which is why I'm introducing both of them. In normalized form, for a jump, and no jump, okay, that's explicitly nonlinear. Then if we write this out, the psi in normalized form V psi is equal to minus I H bar H effective plus a half sum over mu L mu dagger L mu expectation value dt psi plus sum over mu dn mu L mu divided by the square root of the expectation value minus 1 by psi. Okay, so this is a formal way of writing the quantum trajectory that we just wrote in kind of algorithmic form by including these stochastic intervals which happen, you know, in a set of measure 0, we simultaneously have these evolutions. So this is a formal expression of the thing we've been doing for lectures now. But it's a formalism that's useful for extending to the case of quantum state diffusion, which where we are headed. But before I get to that, and the last thing I guess I'll do in today's lecture, because we are out of time, is just to show that this stochastic Schrodinger equation, SSE, stochastic Schrodinger equation, is kind of like a Schrodinger. I mean, without all this stuff, it looks like the Schrodinger equation, right? D psi dt is minus I times the Hamiltonian. But it's got this other stuff in it, which is all related to the fact that we're continuously monitoring the system, monitoring the vacuum. What I want to show is that when I average over all ensembles of this stochastic evolution, I get the deterministic master equation. Better. So let's do that now, and then we'll quit. So let's see what we got. We have that rho at t plus dt is equal to the ensemble average of all the evolved trajectories, evolved according to that, okay? Which is equal to which is equal to rho of t plus the ensemble average of psi with, I'll just put the d inside because it looks better. And now I have to be careful. Because I have a stochastic interval, and because the square of it isn't necessarily 0, I got to keep the d psi's. Of course, all the dt's, they're 0, because dt squared is 0 in a differential sense. But the dn ain't if mu equals nu. Okay, so now, so I can bring this to the other side and get d rho is equal to all right, so now I got to plug it all in. And it's annoying, but let's do it. Let's do this one first. Let's write it down. D psi. This looks nicer. So that's equal to minus I H effective. Well, I'll write it all. All right, H bar. I better check my notes. Yeah, okay, sorry. H effective plus some times rho, okay, dt, plus 1/2 sum over mu expectation value rho dt. That's the first term. And then I have plus sum over mu VNU L mu over the square root of the expectation value minus 1 rho. Okay? Now I have this other term, which is just the conjugate of it. So that's equal to plus I over H bar, H effective dagger dt, plus 1/2 sum over mu, L mu dagger L mu dt rho, plus sum over mu En L mu, I'm sorry, rho L mu dagger over the expectation value minus 1. Okay, that's this term. And I got this term. And that term is, the only term that's going to survive is this. The dt with itself is 0. This with dt is 0 because this is also will be averaged to dt. So the only term that matters is this with itself squared. And then it's only when mu equals nu, so I only have one sum where mu equals nu. So that's then the sum where mu equals nu squared, averaged over the ensemble, L mu over square root minus 1 rho L mu dagger over the square root minus 1. So now what we said is dn squared is dn. And when averaged over the ensemble, I get the probability, which is here. So playing a dirty trick. Well, not so dirty, it's correct, but it's bad in your race. Look at that. Et voila! It works because this cancels this, cancels this. The guys with the minus ones cancel these guys. All these guys cancel. And when all the dust settles, you get, you can check it for yourself, that d rho is equal to minus I over h bar, h effective, commuting with rho in the prime sense, plus sum over mu, L mu, rho, L mu, dagger. Hooray! So, this seems heavy-handed, this formalism for, I mean, well, we introduced all this stuff, I mean, we had this, but where we're headed with this is the case where we're not just going to look at a single photon click, yes or no, we're going to look at cases of macroscopic numbers of photons, where we then can think about this as having certain photon counting statistics. And based on those photon counting statistics, we'll have a stochastic Schrodinger equation, which will take a very nice form. So that's where we're headed, and that's what we're going to do next week. All right?